We are going to finish up this chapter by talking about the context for life in the universe. So let's start with, what happened to make Earth special? Because, okay, let's be honest. In some ways, Earth is very special. We are here, and we are intelligent, and we design and create all kinds of things. What is a phone other than a rock or accumulation of rocks that you electrocuted until it got smart? Anyway, so what happened to make Earth so much different than everything else we observe? Um, we know that comets and meteorites have brought water and minerals to Earth. So that's part of what made Earth special, and yet that will happen on other planets as well. If we look out into the universe, clouds of gas and dust condense to form stars, which have planets orbiting around them. And so, I'm orbiting around. Um, so the minerals that are found in those clouds and dust become really important. What kind of minerals are there? Um, and for human life, the 9 amino acids that we need to find in our diet are listed here on the picture. The specific amino acids are not important. It's what are the chemical elements in those. So C stands for carbon, H stands for hydrogen, O stands for oxygen, N stands for nitrogen. And if we look at this picture, that's basically the only 4 elements on here. It's the combination. And so where do we find carbon, hydrogen, oxygen, and nitrogen that can combine into amino acids? And the answer to that technically is nearly everywhere in the universe. If we look at Earth, we find extremophiles, which are microorganisms that live in extreme environments. So here we are looking at, a river that has a pH of 2, which means that, very acidic. The microorganisms that live in this river love the acid and also create the acid that allows them to continue living there. So an environment that by normal standards life would not exist, except that we find organisms that live there. If we go and look at, in this case, Mars, these are the first 2 drill holes by the Curiosity rover drilling into mudstone. We see that the outer edge of this rock is very red compared to the very gray interior. And that is because of the atmosphere of Mars. So everywhere we go, we find evidence of environments in which life can exist. This is a mudstone, which means that there was water there, so some of the conditions necessary for life. Where should we look in our solar system for life? Well, if we go to Jupiter, remember we talked about tidal heating and how tidal heating stretches and pulls on Io, and makes it the most volcanically active body in the universe, in the solar system. And on the other end of the Galilean moons is Callisto, with nothing occurring on its surface. But Europa here is at a distance where that tidal heating may be just enough to keep the bottom of the ocean liquid and warm enough for life, but not so hot that it's inhospitable. If we look at Saturn, Galileo and Cassini instruments strongly suggest the presence of an ocean under all of this ice. And in this case, it's a salty ocean, which even better for the conditions that we need for life. Cassini watched these plumes being spewed out by the geysers on the southern region of Enceladus. And all of that is venting into space. But what it tells us is that there is liquid water under all that ice. If we look at Titan, the orangey glow from Titan is from its thick atmosphere. If we think about the atmosphere of Titan, mostly nitrogen with methane and some other complex organic compounds. Remember back to those amino acids that I just mentioned? Nitrogen and complex organic compounds. Or complex organic compound means that it has carbon, oxygen, and hydrogen. So we now have all four of the necessary ingredients for basic amino acids. Right here, this glint is reflection off a flat liquid surface, so probably a lake. We see other lakes here on the surface of Titan. So we don't have to go very far in our solar system to find places that have the components for life. Now, the important question is, finding life. So if we look at our atmosphere, we talked about atmospheric windows early on in the semester, and that there are places where wavelengths of light can get through the atmosphere. So if we are looking at Earth, all of these water and ozone peaks and valleys may be possible to be used as evidence of, habitable and inhabited, if without organic processes, life processes on the Earth, we would not have free oxygen in our atmosphere. So the fact that there is molecular oxygen and ozone in our atmosphere could be used as evidence that we have plants, using chlorophyll photosynthesis to produce oxygen, free oxygen in the atmosphere. So if we look at other planets and find the same evidence of, exoplanets, and find the same evidence of free oxygen and water in the atmosphere, that may mean inhabitable and inhabited by life. Remember, life does not mean walking two legs, brain talks to you. Life can be, the bacteria that's, floating around in the raindrops sitting outside on your deck. We have sent messages out. This is the plaque from Pioneer 10 and 11, and then the golden record on Voyagers. So we have sent images out. So let's see, there we go. This represents the distance from us to important pulsars, and then the little bumps represent how fast they pulse, so that other civilizations could figure out where we are in relation to those pulsars. Image of what we look like compared to the size of the radio dish on the spacecraft, a picture of our solar system, and started third rock from the sun and went out, and there's the little spacecraft. So these are supposed to be messages that we've sent out. So then what messages are we listening for? So this is the original SETI group. Frank Drake is, I think, he's on the back row. I think he's second from the left, in front of the very first telescope that they used for listening for messages from space. Over here we see the Allen Telescope Array in California. This is 42 or 43 radio telescopes in an array that they use to listen for signals. So what they're listening for is things that would not be random, because it's very easy to hear pulses and such from pulsars and all kinds of radio sources out in the universe. What we're listening for is things that are not random. And then the Drake equation. This is an equation that suggests how likely it is that we find intelligent civilizations out there. And so each term relates to one component of that possibility. Planets that support life, and then what fraction of those planets has life ever formed, and what fraction of those planets have intelligent life, and what fraction of those planets have a civilization. So most of these are numbers that we don't even know how to give a realistic answer for, because we have one data point, Earth. It's the only place where we have ever found life or intelligent life or a civilization. So the Drake equation is really interesting, and it helps you pinpoint what you're looking for, but it's not even an equation that we can solve yet. So other ways of looking for life out there, the Wide Field Infrared Survey Explorer, that's the name of this satellite. We've used the satellite to search for infrared signatures of construction projects. By that, they're looking for enhanced readings for any of those elements that we think would be created in planet-size construction projects. And the first survey did not reveal anything, but, let's be honest, we can only see a tiny portion of the universe with enough resolution to even be able to consider that we have answered this question. So I want to thank you for listening, and I've had a lot of fun creating these videos, and we'll see about making some more in the future.